Welcome to the Vincent Massey Computer Science Club junior level, and this is the first week of lessons after the introductory C++ learning session. So this is technically week 2, but regardless, let's get started. Today we'll be doing something called binary search. You may have heard this before, whether it's in aspects of computer science or you might even seen it in math. You might know it, just not know what it's called. Or you just might find it intuitive once you see it. You'll probably fall in one of those umbrellas because it's not a hard algorithm to understand, but binary search is a big old log n searching algorithm, and it's primarily used to find an element in a stored array, meaning that its efficiency is much better than just searching for an element by checking all the indexes. And you may have seen this application in terms of warmer or colder. If you take the warmer colder game, and then the idea is to guess a certain number. Let's say we had a set of numbers from 1 to 16, and every time you looked at a number, you said it was warmer or colder, or in this case, to be more like binary search, we'll say, is it greater or less? So if their guess is right, then the game is already over. But if the guess is smaller than the hidden number, there's response is word colder, in the sense of your number is too low, your guess was too low. And then otherwise, if your guess was too high, the response would be warmer, and so your guess is too high. So another idea that you can use this in is finding a word in a dictionary, where you start at the halfway point and then you check, is your set of letters, is your letter greater than or less than a certain letter, like the starting letter and then the second letter and the third letter and so on and so forth, and you'll find your way there. So the idea of binary search is that you take from the middle. Alright, so this is our template C++ code. This is what we did last week. The idea of binary search is to search from the middle. Now, let's see how this is going to work. So let's pull out our whiteboard, and then let's say we have our set of numbers 1 to 16 over here. And we were looking for the third number. Or not the third number, the number 4. And you didn't necessarily know that these numbers were sorted in any way at all. So the numbers could be something like 1, 2, 4, 6, 8, and you'd be searching for 4 or searching for 6 and so on and so forth. But let's just start with a simple example of just every number from 1 to 6, every integer from 1 to 16. Okay, so let's go back. So the idea of binary search, the optimum strategy is to search in the middle. So the middle is actually right here between 8 and 9, and we're looking for the number 4 in the end. So we're searching between 8 and 9 because there's no middle index between two things, we'll just go with the lower one. So our current guess is 8. So first you check, is 8 equal to 4? No, then we haven't found our guess yet. Is 8 greater than 4? Yes. So that means that all these numbers out here that are greater than 8 are eliminated, because you can't choose any number that's greater than 8 because it'll always be greater than 4. Now that leaves 1 to 7 remaining. So now let's check in the remainder over here. Let's look at this part, because now the other half doesn't matter. So we said we go from the middle, right? So now we're checking from 1 to 7, and so the middle number is actually 4. And guess what? We found our number in literally 2 guesses. So let's see how this is going to apply if we chose a different number instead of 4, because 4 we found pretty early on. Let's erase a bunch of this. Okay. And instead, we'll go for 7. Actually, no, let's just go for 9. Okay, So you start with the middle. So you do you find the middle number, and then if it's in between, we're gonna go to the to like between 1 and 16. The average of those is 8.5, and so we're just gonna go right here. And so the number that we're gonna take is this 8. Is 8 greater than 9? No. Is 8 equal to 9? No. So that means we have to search in the right half. So our next search will be from this index to this index. And so that means that all the numbers that are less than 8 and 8 are eliminated, because you can't have any number that's less than 8 somehow be equal to something that's greater than 8. And notice how this 9 over here is the first thing in this list. We can't necessarily do anything about that because that's not the idea of binary search. The idea of binary search is to keep searching by dividing your list by 2, or not your list, you're dividing your the segment that you're using by 2, and then continuously dividing by 2 until you find that your middle number is going to be that value that you're looking for. So now let's look. We have our left is 9 and our right is 16. And so this time I'm actually going to compute the average. So the left is 9 and the right is 16. So 9 plus 16 over 2 is 25. And I'm just one indexing, so we'll show how the 0 indexing works, but for now I'm doing one indexing. So 9 plus 16 is 25 over 2, which is 12.5. So we're going to round that down to 12. So now we're taking this number right here, this 12. And this time, is 12 equal to 9? No. Now what's the case? Is 12 greater than 9 or less than 9? And we see that 12 is greater than 9. So that means that all numbers here are crossed out, because anything that's greater than 12 can't possibly be something that's less than 12. And so now we're left with 9, 10, and 11. I shouldn't use black there. Okay, 9, 10, and 11. And then the middle number in the range 9, 10, and 11 is 10. But 10 is not equal to 9, but instead 10 is greater than 9. So that means that these numbers are eliminated. And then we find out that both our left value is 9 and our right value is 9, which makes the middle number equal to 9 plus 9 over 2, which is 9. So we see the idea of how binary search works. Now we need to see, why is this more efficient? So if we let n be the size, what we effectively did was for every n, for every step, we cut half of the array that we're working with. So that means that the size of the array was n, and then it went to n over 2, and then it went to n over 4, and so on and so forth until we got to 1. That's what we saw with our case with 9. With our case with 4, what we found was that one of the steps was actually leading straight to 4, so we found it really quickly. But this efficiency is asking, to calculate this efficiency, you have to ask yourself, you go from n to n over 2, that's one step. Then from n over 2 to n over 4, that's one step. And then so on and so forth. And until you can't divide your list size by 2 anymore, you keep adding 1, because that's your total number of steps in your worst case. And this basically asks, how many factors of 2 can divide into n? Because every time you're dividing by 2, you're adding 1 to n. And what you see is that this is the definition of log base 2 of n. Log base 2 of n is, if log base 2 of n was equal to x, that'd be saying that 2 to the power of x equals n, where x is the number of steps. So that means that the efficiency of binary search is big O of log base 2 of n. Now, you might be questioning, wait a second, you said that the efficiency was big O of log n at the start. And typically in math, when we define log with no base, it's assumed to be base 10. Well, in computer science, we just defy that rule, and we say that not writing anything for log n will imply base 2. And the reason for that is because there's a lot of algorithms out there that have some factor of log base 2 of n, and almost nothing runs on log base 10 of n. So we'll define log base 2 of n to be log n instead of log base 10 of n being log n. If you didn't learn this in math class, this is usually grade 11, or if you studied ahead. If you didn't learn this in math class, don't worry about it, because now you'll know. But just please don't mix this up in your math classes, because I'll be referring log base 2 of n as log n from here on. So let's see how that's actually implemented. So let's go with a... so I'm not going to worry about fast input here because that's not really necessary with our demonstration. But let's go with a simple vector of int, and we'll call it vals. And then we'll pull, for int I equals 1, I is less than or equal to, and we'll go to 100, I plus plus, and we'll just push back vals dot push back I. So we're having all numbers from 1 to 100. And now we need to do some binary search. So all right, let's just keep going with this. Okay, so what we need, and what we saw was that at every step we had some left value and some right value, and then the value that we're looking for. Int desired value is going to be the desired value that we're looking for. So cn desired value. Whoops. And then our left and right will be the left and right ends of the binary search. Value we are looking for. Okay, so because we start with 1 to 100, and every element at the start is viable, every index is viable, that means that we need to set left to be our leftmost index in the vals array, or vector, which is 0, and our right will be the right end of it. And since there's 100 elements, and we 0 index, we have our right index is 99. And so the idea is to keep running until you find your element, or the element may not exist. But in this case, we're just going to make it so that it exists. But we'll do the general case actually of it might not exist or it may exist. So we'll do while L is less than or equal to R. And the reason I do this, not L, sorry. While left is less than or equal to right. And the reason I do this is because if you're at some point in your array where your left and right are the same, and you still can't find your thing, that means the value never existed. And then either your right will become less than your left, or your left will become greater than your right. Your left would increase by 1, or your right would decrease by 1, effectively having the same problem being it's not possible. And so at that point we can say, hey, something's wrong here. And so we'll have a Boolean of whether our number was found. So while left is less than or equal to right, we need to take the middle index. And so that is int mid equals left plus right over 2. And remember C++ division, default division of integer by integer will result in a truncated value. So we don't need to do the double slash like Python. It doesn't exist in C++. Okay. So now you need to check if your vals at mid is equal to if your vals at mid is equal to your desired value, whoops, then you want to print out we found our number, and we'll just have an end now. And then after, the next case is actually here we'll break out of our while loop because we've already found our number. Now we need to check two things. If vals of mid is greater than the desired value, else, and this is basically saying else if vals at mid is less than our desired value. We'll put this bracket out here. Okay, so our choice was too high. And so in the case that our choice was too high, we want to bring our choice, or bring our right side down one. And the reason we do that is so we can search in all the possible values that are less than vals at mid. So that's simply saying right equals mid minus 1. Because we don't want to include mid because it's useless. And then otherwise, left equals mid plus 1. And then that should be good. And so we'll actually put here that found equals true. And then now we can come out here and say if not found, then we will print out that we didn't find our number. And let's test this out. Let's say we're finding 50. We found our number. And then now let's put a number that we didn't put in our thing. Let's say 101. We didn't find our number. Now let's see how fast this was. And to see how fast it is, it's simply doing int steps equals 0. Here we increase our steps if we didn't find our number. So out here would be steps plus plus. Whoops. And remember, this is the same as doing steps plus or equals 1. And actually, divided by 2 is technically considered a step, so let's actually put it out here. Steps plus plus. And so now we'll go out here and say cout, whoops. It took us, and then a number of steps, put a space there, to determine this. And then we'll wind out from the end line. Get that out of there. And we should be good. So now let's test 50. We found our number, and it only took us 1 step. Actually, I didn't even put steps in here. And the reason it took 1 step was because 50 was actually right in between 1 and 100. So we just got lucky. Now let's check 51. It took us 6 steps to determine where 51 was. And so that is much, much faster than just trying to find 51 normally. Because if you were just to do number of steps normally, you'd have to check vowels at 0, vowels at 1, vowels at 2, vowels at 3, and so on and so forth, all the way to 99. So your worst case scenario would be big O n if you search normally. But since we're dividing, we see that it's big O log n. See, clearly, we can see that 2 to the power 6 is 64, and 2 to the power 7 was 128. So we're around the ballpark of big O log n. So that, once again, gives an example of why we're finding a value and why is it working. And so what we need to discuss now is the applications of binary search into certain things. So binary search doesn't necessarily have to be used on numbers. The conditions for using binary search is that what you're working with has to be sorted, because you're always doing something with greater than or less than. And side note, you can compare strings too by their lexicographic order. So yes, you can use binary search that way. So that's the idea of binary search, and I think I made it clear for you guys. But let me know, either send me a message or leave a comment on the YouTube on this YouTube video, preferably sending me a message via Discord. Let me know if you have any questions. I'll be posting homework or questions to practice with this in a few weeks. And remember that, not a few weeks, few minutes. And remember that I'm not necessarily saying that all binary search problems are this easy, and they're not. But this is the foundation of binary search, and you can go further with it. And actually, there's some, if you want to do some more of your own research, you can find that certain containers, such as sets and vectors, have built-in binary search things called lower bound and upper bound to find the first element that's greater than your current one, or the element that's less than your current value or what you're working with. So it doesn't necessarily have to be using this algorithm all the time, and it's going to get more complicated, but this is a foundation that you need to solve many, many problems, because binary search is always going to have the idea of divide it into and then look in one. And so the conditions aren't necessarily going to be this easy to solve, but some problems might be. You never know. If they are, maybe you can get them pretty easily. But if not, then just apply binary search in different ways and make sure that you're testing your things. Because if you do something like if vowels of is greater than or equal to desired value, or something that won't, you can make very, very easy errors in this. So I recommend you try to debug and write out your code if you're having problems with binary search. And yeah, this is your lesson for the day. It's pretty short compared to what lessons used to be, but I want these to be more of you guys solve the problems instead of I do it. So there will be a document that goes through all these this stuff. And yeah, this is the lesson for this week, and can't wait to see you next week. Yeah, so bye guys.